Okay, so far in this course, we've discussed Feynman diagrams for rather simple sorts of theories. So in particular, we've derived the Feynman diagram prescription for the computation of correlation functions or scattering amplitudes for very simple theories, and in particular only for theories of scalar fields. So we focused primarily on phi cubed theory, where you have a trivalent vertex. There's simple generalizations, for example, to phi to the fourth theory, where you have a vertex where 4 scalar field lines can come in at an interaction point. We discussed also briefly theories where you have more than one scalar field. But really, what we're interested in studying in this class are more complicated theories, such as those involving the fields of the Standard Model. In the Standard Model, of course, only one of the fields, the Higgs, is a scalar field. All of the other fields, such as those describing the various force carriers and matter particles of the Standard Model, are more complicated. They have spin, they have charge, and in order to understand how to compute things in the Standard Model, for example, using Feynman diagrams, we need to understand how to incorporate all of these extra little pieces of data about the spin or the charge of a particle into our Feynman diagram prescription. And all of this is mostly straightforward and is mostly a sort of simple generalization of the types of Feynman rules that we've already seen in this class. When you talk about quantizing spinor fields, so quantizing fermions, it actually turns out there's one quite important subtlety, which I think we'll discuss next class. But by and large, for the other sorts of fields that we might be considering that aren't spinors, the Feynman diagram prescriptions are reasonably straightforward. But what I thought I would do today is just consider a particular theory that is scalar quantum electrodynamics, which is a theory that we've actually already met. We wrote down the action for it, and just discuss in detail the sort of modifications to the Feynman rules that we would need to include when we study perturbation theory in scalar quantum electrodynamics. And this is really just as a warm-up to the full theory of quantum electrodynamics, which we'll start tackling next class. But rather than trying to do the theory all at once, so for example, if you look at the way that your textbook is organized, he really kind of just starts by writing down the Feynman rules in QED, including spinors and vectors and charged particles and all of that stuff, without, and that's kind of a lot to handle all at once. And so the way that I've structured things in this course is first we sort of did scalar field theory in a lot of detail, and now I'm going to do one sort of example of sort of intermediate complexity, namely scalar quantum electrodynamics, before working our way up to the full glory of quantum electrodynamics. Because there's a lot of sort of small subtleties and modifications for the Feynman diagram prescription that we're going to need to end up including when we talk about quantum electrodynamics. And scalar QED is a nice sort of intermediate case where you can understand some of these subtleties without having to deal with all of the sort of full glory of quantum electrodynamics. Okay. So let's just start with the theory that, excuse me, we've discussed several times so far in this course, namely a theory of a single complex scalar field. Okay. So the Lagrangian of this theory, well, let me just write it down for you. It's something that we've studied in class as well as in problem sets several times. So the free complex scalar field, actually, you know what, let me rewrite this explicitly so that we've got all of our phis and phi bars. So you have a kinetic term, d mu phi bar, and then you have a mass term. And then you could imagine adding various sorts of interactions to the theory. So I'll call L int the various interaction terms. And of course, as you know, phi is an operator that creates a particle, but it creates a charged particle. There's a conserved quantity associated with the rotation symmetry, where we multiply phi by an overall phase. And because the Lagrangian is invariant under this phase rotation, that means there's a conserved quantity which we can which we could call charge. And the operator phi has positive charge in the sense that you can interpret it either as creating a particle which has positive charge, or you can interpret it as removing a particle, or I suppose I should say an antiparticle, which has negative charge. In either case, if you interpret phi as creating a particle with positive charge or as removing an antiparticle with negative charge, no matter what it does, it increases the charge of your system by 1. So the operator phi acting on a state increases the charge of that state by 1 unit. And if you want to write out the statement that phi creates a particle or removes an antiparticle a little bit more precisely, we just need to remember the treatment of the scalar field in free field theory, where you expand your complex scalar field in terms of a raising and a lowering operator. And I remind you that because phi is not a real scalar field, as an operator phi is not Hermitian, which means that the raising and lowering operators which appear here are not Hermitian conjugates of one another. So if, for example, you interpret B as the operator, B dagger as the operator that creates a particle, then A is interpreted as the operator as a lowering operator, and in particular, it's an operator that removes an antiparticle. And what I would like to do is imagining how we would modify our Feynman rules to account for the fact that we now have a complex scalar field with this conserved charge associated with it instead of a real scalar field. Okay. Any questions before I continue? So this is something that I think we've discussed a few times before. So if we wanted to study this theory, where we now include an interaction term, we could then imagine going ahead and computing correlation functions as we did in a real scalar theory by studying the partition function, and in particular by introducing what is known as the generating function, which encodes all of the various correlation functions of the theory. And now, rather than introducing a generating function of a single real source term j, we could introduce now a generating function that depends on a complex source j, which is coupled to our scalar field in a way that generalizes the real scalar generating function in a sort of obvious way that is consistent with charge conservation. So in particular, as you can see here now, this source term that I've introduced here is still invariant under the charge rotations where phi goes to e to the I lambda times phi, provided we assign j, we declare that j also has positive charge in the sense that under a charge conjugation, under a charge rotation, j is taken to go to e to the lambda j as well. And so one could go ahead and repeat the entire derivation of Feynman rules that we did for a real scalar field for a complex scalar field, and you would essentially follow all of the identical steps. Okay. Now, I don't want to go through and repeat the entire derivation of Feynman diagrams for a complex scalar field, because the argument would be almost identical to that for a real scalar field. Instead, what I think I'll do is I'll just sort of state what the answer is and what it looks like. And then if things are unclear, you can ask questions, or if it's really unclear, I would encourage you to go and try and derive all of these statements yourself, just by repeating the derivation of Feynman diagrams now for a complex scalar field. And gradually, we're going to introduce slightly more and more complicated examples. So I'm first starting out with a complex scalar field so that we can understand how to incorporate charge into our Feynman rules. Later on this lecture, I'll introduce a vector field. I'll couple this to electromagnetism. Think of a scalar QED so that we can understand how to incorporate the polarization vector of the photon into our Feynman rules. And then starting next class, we'll study the full glory of real QED, where we can incorporate the spin of our particle into our Feynman rules. Okay. So that's just sort of where we're going. So the Feynman rules would allow us to compute, for example, the two-point function. So the two-point function is actually something that we've already computed just in free field theory. So in free field theory, this two-point function, well, the first thing to notice about this two-point function is that it is almost exactly the same as the two-point function. So let's say if this first one is phi bar of x and this is a phi of y, this two-point function is almost exactly the same as the two-point function of a real scalar field. The only difference being that the two-point function is now not the phi two-point function, but the phi bar phi two-point function. Remember that phi is an operator that has charge +1, and so phi bar is an operator with charge -1. The vacuum state has 0 charge. So if you want some non-trivial expectation value, then the things that you need to be taking the expectation value, the charges have to cancel. Okay. So for example, the expectation value of phi times phi, the expectation value of phi times phi is going to be equal to 0, because phi has charge +1 and the charges don't cancel if you take a phi expectation value. But the expectation value of phi bar phi is not 0, and it's equal to the usual two-point function of a free scalar field. So if you wanted to interpret this in the language of Feynman diagrams, this means that there is a propagator out of which we should build our Feynman diagrams, but it's a propagator that does not connect a phi with a phi, but instead it connects a phi bar with a phi. Okay. So in particular, if you introduced one source term which was associated with a phi bar and another source term which was associated with a phi, then you're allowed to have a propagator only if that propagator connects a phi bar with a phi, not if it connects a phi with a phi. Okay. So this is the propagator that in position space we would just write as t of phi bar x, phi of y. Or in momentum space, we would write it as I over p squared minus x squared. And so what we're going to do, in order to keep track of the rule that you can only have a propagator that connects a phi bar with a phi and not a phi with a phi, is I'm going to put a little arrow on this propagator. And this arrow is referred to as a charge flow arrow. And in particular, its role is to indicate which direction charge is flowing in this propagator. And in particular, it will point from an operator of minus charge to an operator of positive charge. This is also sometimes called a particle flow arrow, because it's pointing from the thing that creates an antiparticle to the thing that creates a particle. And the point is that these charge flow arrows, when we write down our Feynman diagrams, will help us keep track of charge conservation in the theory. Okay. So let me give you an example which sort of demonstrates how that works. Okay. So in particular, what I want to assume is that the interaction term that we're using to perturb our theory with respects this symmetry, so the phi to e to the I lambda phi symmetry, then that means that all of the various interaction vertices that you'll get in your Feynman rules will conserve charge. Then that means that in the Feynman rules, we have to match up, we have to ensure that all of the diagrams, or all of the vertices appearing in the diagrams, conserve charge. And when we do so, we're going to end up matching up the charge flow arrows in such a way that every interaction vertex, if an interaction vertex has a particle of plus charge coming in, then it has to have another particle of plus charge coming out. Okay. So, for example, let me just give you a very simple example which hopefully will make it clear exactly how this works. Okay. So let's take the case where your interaction vertex is, say, phi bar phi quantity squared. Okay. So that would be phi squared times phi bar squared. Okay. And I suppose we could put a g here. So that would be your coupling constant. And in order to keep all of the combinatorial factors sort of convenient, we'll divide by 4 here, because that interaction term has two symmetries. You can interchange the phi bars with one another to get a factor of 2, and the phi's with one another to get a factor of 2. So this would lead to a type of interaction vertex in your Feynman diagram. And it's an interaction vertex where two particles, well, it's a interaction vertex which gives you a factor of Ig, the coupling constant, and two particles of plus charge can come in, and two particles of plus charge can go out. Okay. So, for example, if you were to try and study the Feynman diagram expansion in this theory, so this is a phi to the 4th theory, and the Feynman rules in this theory are a little bit different from the standard real scalar phi to the 4th theory, in the sense that you now have these little arrows attached to your Feynman diagrams, and when you write down contributions to scattering amplitudes or correlation functions, you need to make sure that these arrows align. Okay. So, for example, if you wanted to compute, say, a 2-point function, a phi bar phi 2-point function, then you would have one contribution that looks like this. That's the free result. But then you would have another contribution that looks like that. Okay. Hopefully you can sort of see what I've done there. Let me give you a slightly more sophisticated example, one which will be very similar to the theories a little closer to electrodynamics. We could consider a second theory of a real scalar chi coupled to a complex scalar phi, and we could take, say, the usual action for our real scalar field chi and for our complex scalar phi, and then we could add an interaction term And so let's add a term of the form chi phi squared. And in order for that term to be invariant under the charge rotation symmetries, it needs to be a chi phi bar phi. Then if we wanted to compute scattering amplitudes in the theory, we would have two different types of propagators. So I'll use a dotted line to denote a chi propagator, which is given by the usual formula of I p squared minus m chi squared plus I epsilon. And then we would have a phi propagator, and we have to put a little arrow there to indicate which direction charge is flowing. But aside from that, the value of the propagator is, so let's call that m phi squared, is exactly the same as in a real scalar field theory.
Is the kinetic term complex field in Lagrangian positive?
Yes, sorry. Forgot about that. Thank you. Good. And then the interaction term. So here, the interaction term comes from this guy here, and it says that one chi particle can go and turn into a phi bar and a phi. Okay. So that means you'll get an interaction term that looks like this. And that will give you a factor of I times the coupling constant. Okay. And the important point is that you're not allowed to have an interaction term that looks like this, where two particles come in with opposite orientations. Okay. That would correspond, so for example, if phi is the particle that, if phi is the field, for example, that creates an electron or destroys a positron, then this diagram, for example, could lead to a process where one chi particle forms an electron-positron pair, which is something that conserves charge, whereas this diagram would describe, say, a chi particle which decays into an electron plus an electron. Okay? And that's a process that violates charge conservation. So you can see that these arrows that I'm using to mark up our Feynman diagrams are, all they're doing is they're enforcing charge conservation. Yes, question?
So in this diagram that you just drew, would interchange of those two arrowed lines be a valid symmetry, or would we not count that?
We would not count that as a symmetry because, indeed, excellent question. When we talk about the symmetries of a diagram, we mean a symmetry that also, when we compute symmetry factors, preserves all of the additional structures that we use to mark up a Feynman diagram. Okay. So, for example, here we have a simple charge scalar field, so we're marking it up with arrows. In other more complicated theories, there might be more complicated pieces of data that you use to mark up a Feynman diagram. Okay. Excellent question. Very good.
For symmetries, does that mean that for the one up there where you had this loop, you could do the loop in the other way?
That's exactly correct. So this, you're allowed to have this guy, but not, for example, let's see, I just want to make sure, not that guy, right? Oops, sorry. I can't, yes, not that
Not
guy.
allowed to have that guy? It's not a symmetry?
Oh, no,
Because it's the same, right? It's
oh, it is
like-
the same, yes, sorry, no. That what I said just didn't make any sense. Yeah, so for this guy, you still do have that, yes.
It's connecting to the same point, so...
When you would
Oh, wait, I'm sorry. That diagram, so, yeah. Yeah. Yeah, I mean, so the vertex, so sorry. So what you need is you need the vertex here. You need it to look like you have, so you need one particle going in and one particle going out, right?
Yeah.
And so they're both allowed, right? So you can either have them going out like that, or you can have them doing the opposite thing, which is what we had down here. Okay. Hopefully that's clear. So they're both allowed,
Yeah.
but they're different Feynman diagrams.
So they're not a symmetry of one another.
Yeah, well, the actual numerical value of those Feynman diagrams would be the same, okay? So, but yes, but they would technically be counted as different Feynman diagrams. Good question.
So we use symmetry factor for this.
Well, there would be two different ones, and neither of them would get a symmetry factor. Right? Good. Great. Sorry. Yeah. Good. So the important point is that the momentum space Feynman rules are just as for a real scalar field, just taking into account that we have two possible types of incoming particles or outgoing particles. Okay. So for example, let's just consider the following process. Let's say that phi is the operator that creates a positron or removes an electron. Okay. So this would be a simple version of a theory of electrons where we're neglecting the spin of the electron. Then let's say, excuse me, that you wanted to compute, say, the scattering of an electron off of an electron in this theory where the electron is the phi field and we have some other field chi that interacts with it. So what sort of diagrams would contribute to this? Well, the amplitude for this process, so the thing that we usually call I times m, well, you would get the usual tree level thing, the usual you would get the usual terms with no interaction, where you just have a bunch of free propagators. But you would also get a term that looks like this, say, where you have, so here, as, sorry, it's not a very nice looking Feynman diagram. Let me redraw that so it's a little neater. So here, as with a real scalar field, I'm going to use the notation that the incoming particles are all arranged on the left and the outgoing particles are all arranged on the right. So here you have two ingoing arrows. So the ingoing arrows are the things that are telling us that we have incoming positrons. And here these outgoing arrows denote the fact that we have outgoing positrons. Okay, so the arrow points in the direction of charge flow. And here we have a contribution to the scattering of two positrons off of each other via the interchange of one of these chi particles. Similarly, we have another diagram that looks like this. So this is a little harder to draw. This is what we call the U-channel diagram. When we discussed 2-to-2 scattering in phi cubes theory. So this is what we call the T-channel diagram, and this is what we call the U-channel diagram. But one of the things to note is that now that we have charge conservation, there's no S-channel diagram. So there is no S-channel diagram, because what was the S-channel diagram? The S-channel diagram is one that looks like this. And that would require us to violate charge conservation at one of these vertices. Right? So this is a very simple example of how the Feynman rules for charged fields are very similar to those for real fields, but the sorts of Feynman diagrams that contribute are often slightly different. So in particular, for phi cubed theory, we had what we called crossing symmetry, which was the observation that all of the scattering amplitudes were invariant under permutations of the Mandelstam variables S, T, and U, and that's no longer going to be the case once you start mucking around with charged fields. Okay. Similarly, let's imagine that we wanted to compute a scattering, a process where an electron and a positron come in and an electron and a positron go out. Well, what sort of diagrams would contribute to this process? Well, the incoming particles will be arrayed on the left. God, I really can't tell left from right. Will be arrayed on the left. So if you wanted to describe an incoming positron, you would look at a Feynman diagram with one incoming charge arrow on the left, and an incoming electron will have an arrow that's pointing towards the left rather than towards the right. And so one possible Feynman diagram you would get would look like this. Okay. So here, this arrow here refers to the incoming electron. And this incoming electron, well, it has the charge flow arrow, or the particle flow arrow, pointing to the left rather than to the right, indicating that it's an antiparticle that's an incoming particle rather than a particle. Remember, these arrows point in the direction of charge flow. And so there'll be another diagram, which is the T-channel diagram, which looks like that. So here, one of the nice things about this picture is that these two diagrams that we're writing down, they both sort of have various sort of physically intuitive stories that you can attach to them. The S-channel diagram is telling the story of an electron and a positron that come together, they annihilate, they form a chi particle, which could be a photon, and then that photon then decays into an electron-positron pair. Whereas the second diagram describes a positron up here on the top and an electron down here on the bottom that interact via the exchange of one of these chi particles, one of these photons. And just as when we considered, positron-positron scattering, there was no S-channel. Here, if we study positron-electron scattering, there's no U-channel. Okay. And indeed, okay, so a question for the class is what process would you consider? So here we found one process which is up top, which has only T and U channel, one process at the bottom which has only S and T channel. So there's going to be another process which has no T channel. And so maybe exercise tonight as you're trying to fall asleep just to figure out what that process is. Okay. Another final comment is that, for example, with these rules, some sort of scattering process where you take a positron-positron pair and try and form an electron-electron pair, that process is impossible. Now, if you just thought about it intuitively, well, that process would violate charge conservation because you start out with a state with 2 units of charge, and you end up with a state with minus 2 units of charge. And I just sort of challenge you, start trying to draw Feynman diagrams of the following form. So what would a Feynman diagram look like, which described a positron-positron becoming an electron-electron? Well, it would look something like this. You would have two incoming positrons over there on the left, and you would have 2 outgoing electrons, which would be described by particles on the right, legs on the right, which have their charge arrows pointing in. And I challenge you, this is actually probably a sort of nice exercise in graph theory. I challenge you to prove that there is no such graph with that property. And in order to prove that, you'll need to use the fact that all of the various interaction vertices that you would use to build up this Feynman diagram all conserve charge. They have the same number of arrows going in as they have going out. Okay. So that would sort of be a fun exercise in graph theory. Good. Okay. So I just sort of wanted to spend a little bit of time talking about the theory of charged particles and Feynman diagrams with charged particles, just because there's this sort of notation where we have these charge flow arrows can get a little bit confusing. Because very often, you know, previously we used arrows to mark up our Feynman diagrams, but the arrows that we used previously were momentum flow arrows that indicated which direction momentum was flowing. And these are not the same as charge flow arrows. So the charge flow arrows are not the same as momentum flow arrows. Remember, we use the convention that momentum is always flowing from left to right. And so unless there's some ambiguous case, so let's say that I was looking at one of these T-channel diagrams up above, if I needed to write down the momentum of that leg right there, I would need to tell you whether I was taking it to flow up or down, because, you know, just using the rule that momentum flows from left to right, I can't tell you what direction momentum is flowing in that leg. But generally speaking, we will try and suppress the arrows that tell us which direction momentum is flowing, but we will have to write the arrows that tell us which direction charge is flowing. Good. Okay. Really, that's all I wanted to say about charge flow arrows in Feynman diagrams. This is really, you know, the first example of a sort of thing that we're going to have to encounter more generally, which is that when you have multiple fields in your theory, you're often going, that means when you have multiple species of particle, you will often have to introduce different notations to distinguish these different species of particles as they run around in Feynman diagrams. And indeed, we're even going to have to be a little bit more subtle when we talk about particles which carry spin. So what about particles with spin? So the simplest theory of a particle with spin is not actually a spinner, but in fact the electromagnetic field. And so what I'd like to discuss next is a generalization of the theory of a complex scalar field to couple that field to electromagnetism. And the action for a complex scalar field coupled to electromagnetism is something that we wrote down earlier when we discussed the gauge principle. So let me just remind you of where that action came from. The idea is that we identified the charge rotation symmetry phi goes to e to the I lambda phi of the complex scalar field with the gauge symmetry where the gauge field A is shifted to A plus the derivative of some gauge potential lambda. We identified gauge symmetries with charge rotation symmetries. And we found that the full Lagrangian, excuse me, the full Lagrangian that we wrote down here was gauge invariant, provided we coupled the scalar field to the electromagnetic vector field in a very particular way. In particular, the kinetic term now doesn't involve the usual derivative, but instead involves what's known as the covariant derivative, which couples the complex scalar field phi to the electric field, or to the electromagnetic field in this particular way. Good. So again, this theory can be studied in perturbation theory using Feynman diagrams. The coupling constant now that describes the strength of interactions in the theory is the electric charge E. If E is equal to 0, we just have a free electromagnetic field and a free complex scalar field that don't talk to each other. And so when we use Feynman diagrams, we're going to do perturbation theory in the coupling constant, which is the electric charge of the complex scalar field. And in principle, excuse me, in principle, for example, correlation functions can be computed just as they were for the real and the complex scalar field by taking variational derivatives of an appropriate generating functional. So for a real scalar field, this was a function of a single real source J. For a complex scalar field, it'll be a function of a complex source J. So I've denoted J and J bar separately here to remind ourselves that J is complex. And if you wish to include the effects of electromagnetism, you also need to introduce a source, J mu, for the electromagnetic field. And so then this, at least in principle, is computed by doing a path integral, where we integrate not just over the value of the scalar field, but also the value of the electromagnetic field. And you weight this by an action along with our source terms. So you have a J phi bar plus J bar phi. And the source term for the electromagnetic field is just J mu A mu. And just as one can compute correlation functions by taking variational derivatives with respect to J to pull down factors of the scalar field, by taking variational derivatives with respect to J mu, you can pull down factors of the electromagnetic field for vector A mu to compute those correlation functions. And more or less, all of the various indices, the derivation of the Feynman rules for scalar quantum electrodynamics goes through just as it did for the real scalar field or the complex scalar field, just with a couple of modifications that I'm going to point out. So the first modification is that the propagator, so the two-point function of the vector field A is now an object that has two indices. So unlike the scalar field, which had no indices, we now have these two mu and nu indices that arise when we take the two-point function of the vector field A. So really, you should think of this two-point function as a set of 16 quantities labeled by those two indices mu and nu. And this is the integral. So this is something that we computed, this two-point function. And it's the integral d4p of e to the ip x minus y, again with this normalization factor, 2 pi to the fourth. And the propagator is minus I times g mu nu over p squared, along with the usual I epsilon factor. So this quantity here in parentheses is the propagator in momentum space. And one of the one of the important points, and it's something that I don't think I'm going to go into in too much detail right now, although when we come back and next semester do the quantization of Yang-Mills theories and gauge theories, it's something that we'll have to discuss in a great deal of more detail, which is that this propagator depends on the choice of gauge. In particular, I remind you that under a gauge transformation, A shifts by the addition of d mu lambda, where lambda was your gauge parameter. And so what that means is that this two-point function itself depends on a choice of this parameter lambda. Okay? And so it's not surprising then that the form for the propagator depends on the choice of lambda. So this form where the propagator is proportional only to the metric is a form for the propagator between two photons in a particular gauge known as Feynman gauge. There are other choices that will make the form of the propagator look slightly different. For the time being, I think in order just to write down the Feynman rules as efficiently as propagator, I just want you to take, I just want to stay and live in Feynman gauge, probably for the rest of the semester here. But when we come back next semester and study propagators and gauge dependence in more detail, we'll actually see that you can write down somewhat more general forms for this propagator. But the essential point really is that if you fix a gauge, any physics should be independent of your choice of gauge parameter lambda. And so what we've done here is we've chosen a clever gauge parameter to make this propagator as simple as possible. And all of the answers for any physical quantities that we get at the end of the day will not depend on this choice of gauge. Okay? That's something that we discussed in a little bit of detail when we did the quantization of the electromagnetic field. It's not something that I think we want to spend too much time on right now. But let me just pause and see if there are any questions. So, yes?
There are basically two kinds of sources. One like JMU, which is like the source for the like
That's right.
And the second is
That's right. So there's now two kinds of sources. Okay. So again, there's also a propagator for phi, which is the same propagator that we wrote down above. But now the interaction terms well, what are the what are the interactions? The interactions come from expanding out this term in the Lagrangian, including this coupling between the scalar field phi and a mu. Okay. So in particular, if we just expanded this guy out, what would you get? Well, you would get the usual kinetic term for phi. Then you get something linear in the electric charge. And this describes the coupling between phi and it describes a coupling term that's linear in A and quadratic in phi. And indeed, you can recognize this term here as the conserved current, the conserved Noether current associated with the charge rotation of the field phi. And then finally,
There's no two phi bars, right? On the dmu phi phi.
yeah, is there, I think I got that right? Oh, sorry, good. Sorry about that, yes. And then finally, there's a term, so remember we're plugging in, where did I write it down? We're plugging in this term here for the coupling here. So there's a term proportional to E squared. So there's an E squared, a mu, phi bar phi. Okay. Good. So there are now two different kinds of interactions. So there'll be a trivalent vertex coming from the term linear in E, where one photon, for example, is allowed to decay into an electron and a positron. So if we denote, so let's denote by, so the propagator for the photon, I'll denote with a squiggly line. So this will be the photon propagator. So that is what it would look like in position space if I wanted to compute a correlation function. Or if you wanted to write it in momentum space, you would strip off those dots at the end. But you would have to remember still that there are mu and nu indices, so that tell us that this propagator takes a photon a mu to another photon a nu, possibly with different values of the index. And in momentum space, what was that propagator? It was minus I g mu nu over p squared. So in fact, in the gauge choice that we've chosen, the propagator just takes A0 to A0, A1 to A1, A2 to A2, and A3 to A3. But in fact, it turns out that there are different gauges where that's not true. But this simple gauge, the one that we're going to use in this class, is the one where the propagator is just proportional to g mu nu. But now we have various interaction vertices. So there'll be one interaction vertex coming from this term here, where a photon can turn into an electron and a positron. So that'll give you an interaction vertex that looks like this. And that vertex will be proportional to the coupling constant, so it'll be proportional to minus I epsilon I times the electric charge. But there's one thing that's a little bit subtle about this interaction, which is something new and that has arisen here, and this is the first time that we've seen it, which is that in the interaction term, we have taken some derivatives of the field here. And so this is what's known as a derivative interaction. Now, in fact, what you do when you have a derivative interaction is a little bit confusing if you think about the theory in momentum space. But if you remember our derivation of Feynman diagrams it's a little confusing if you think about it in position space. But if you remember our derivation of Feynman diagrams in momentum space, every time you have a factor of a derivative, in momentum space, that just brings down a factor of the momentum. Okay. So in momentum space, the derivative is just I times momentum. Excuse me. So each time we get a derivative here, we need to include a factor of the momentum of the field that you're taking the derivative of. Now, in order to write down this vertex then, I need to tell you about the momenta of the particles. So I'm going to put our momentum flow arrows here. So I'll call that momentum here P1 and this momentum P2. And also we have an incoming photon which has an index. So I need to label this diagram by that index. And now there are two different interaction terms here. And so you'll get two different contributions coming from this Feynman diagram. And these two different contributions come from the derivative hitting the two different fields. So in this conserved current, in one of the interactions, it hits phi, and in the other interaction, it hits the phi bar. And so you'll get the sum of these two momenta. Okay. Now, actually, going through and keeping track of all of these signs here, excuse me, is a little bit tricky. In fact, there's a problem that I've assigned you on the problem set that's due Friday, where you derive Feynman rules, including derivative interactions, keeping track of all of the careful signs. And it's only by keeping track of all of the careful signs that you're going to be able to come to a sort of very elegant conclusion. So I don't think I'm going to go through the argument in complete detail here, because you're going to go through it for your problem set anyway. But I'll just say that, as hopefully it's clear, that every time you have a derivative interaction, you bring down a factor of the momentum. And then you have to go through the derivation of the Feynman rules a little bit carefully to make sure that you get all of the signs correct. So, for example, if you had oriented your charge flow arrows slightly differently, or your momentum flow arrows slightly differently, so that they were pointing all to the left instead of to the right. Sorry, it's so that they were pointed all to the right instead of arranged in the way that I've done in this diagram here. You would get a factor of minus IE times minus P1 mu plus P2 mu. So the rule that one needs to keep track of when writing down these derivative interactions in scalar QED is that in one of these interaction vertices, you get a factor of minus I epsilon with a plus sign for each momentum that flows in the direction of particle flow, and a minus sign for each momentum that flows opposite to the direction of particle flow. Okay? And that really comes from this relative sign here. It comes from the fact that we have a relative sign between those two terms. And so I should probably emphasize that, as I said before, we're typically going to try and not write down any momentum flow arrows. So when we can, momentum is just going to flow from left to right. So we really only ever write down the particle flow arrow explicitly. And just remember the rule that momentum flows from left to right. Good. Okay. So finally, we have one more type of interaction, which comes from this term here. So that's an interaction where two photons become an electron and a positron. So that means you have a vertex like this. Again, because of momentum conservation, because of charge conservation, you have one charge flow arrow coming in and another charge flow arrow going out. And this is equal to I E squared times G mu nu. It's a G mu nu because, well, I've written the mu and the nu indices separately here, but you can see that in this expression for the interaction vertex, the A mu is contracted with A mu, so that's really, you could write it out explicitly as A mu nu times G mu nu. And the other comment that I'll make is that, remember when we did the combinatorics of the Feynman diagrams, it was important that I divided each coupling constant by the number of symmetries of a term in the Lagrangian. And this term here is invariant under permutation of the two photons. So that means that if I were really normalizing things carefully, I would, in the usual convention, I would put a 1/2 in front of this term. And because I haven't done that, I really need to include a factor of 2 here. So in fact, people give a name to this. They call this the seagull diagram, or the seagull vertex. I think it's supposed to look a little bit like a seagull, but I'm not quite sure. Doesn't really look much like a seagull to me. Good. Okay, so these are the Feynman rules in scalar quantum electrodynamics. I want to discuss one more subtlety of this theory, but before I do so, let me pause and see if there are any questions. Yeah. The I comes because remember whenever we have, I mean it's sort of important, remember whenever we have a diagram we always get a factor of I coming from it. Really, whenever you have an interaction vertex, you always get a factor of I. That's just the rule. It really comes from the fact that in the path integral it's e to the I times action. I think the question that you might have is that whereas we had an I here and we had an I here, you might have thought that it's that I that led to the I down below. But that's not actually true. That I sort of gets disappeared because it's an I times a derivative that's equal to a momentum. Okay. Yeah.
The I's came from canceling the I's in the action, right?
Oh well the overall I's came from the action. Yeah. So the fact that each interaction vertex gets an I is because in the action, you expand out the action. You take the exponential of the action, you just literally expand it out, and every time you pull down a factor of the action, there's an I in front.
Right, and that would come, you would pull it down 4 times here, right? Because you want.
That's.
I should cancel it because you bring it down.
No, remember, I'm pulling down one E here. Okay, so I'm just pulling down one copy of this term.
Right, but in the E squared term.
Mm-hmm. I'm pulling down one. I'm pulling down this term.
Yeah.
I'm pulling down one of those terms. I'm imagining exponentiating that
Right.
and looking at a term of order E squared.
Right.
That is, 1 plus I times this term right here.
Oh yeah.
Right? Okay. Good. Good questions? Excellent. Any other questions? Sorry, there's a lot of details. This is one of those lectures on details, right? There's a lot of details that go into understanding how to actually do computations with these Feynman diagrams.
So if you're only looking at diagrams to order E, you wouldn't consider that
Absolutely.
second.
Yeah. I should point out this final term that we're writing down here is really pretty interesting because you would have thought that if you take a field and you couple it to electromagnetism, the coupling is A mu, J mu, right? That's Maxwell's equations, right? Maxwell's equation says that, grad F mu nu is equal to J nu, and that comes from this term of order that arises from the A mu, J mu term. This term here is really, you should think of it as a nonlinear correction to Maxwell's equations. Okay? I mean, it actually is a very, very important term. This is the term that is responsible for the Higgs mechanism and for superconductivity. Because if you imagine that you had a theory where phi was just a constant with some non-zero value, this would look like a mass term for A mu, A mu. This is why the force carriers, the strong and electroweak force-carrying particles, the W's and Z's and gluons and so forth all have mass rather than being massless. And this is also why a photon is effectively massive inside a superconductor, because you have a complex field phi, which is built out of electron-Cooper pairs, which has some non-zero expectation value. So hopefully in the next week or two we'll get into that in a little bit more detail. But that second term there is really sort of interesting, important, and a little bit mysterious from the point of view of electromagnetism. Yes?
You said this term is equal to this A mu,
Yeah, so A mu is just A mu, A nu, G mu nu. And then of course we have a phi bar phi. Yeah.
Okay.
Yeah, good. Yes. Good. Excellent. Any other questions? Okay. Now, there's one final thing which we need to keep track of when we study scattering in electrodynamics. which is we need to remember that if you're studying, for example, a scattering of, say, some scattering process involving photons, we have to remember that photons have polarizations. And so when I say I have a photon with a given momentum, I'm not uniquely specifying the state of the system. I have to tell you also the polarization of the photon as well. So in particular, if you take the electromagnetic field, A mu, and you think of it as being expanded in terms of raising and lowering operators, then really, as we discussed before, you should think about a sum over possible polarization states. Did I call them I? I might have called them R or S. I'm pretty sure I called them R and S, talking about polarizations of spinors. I think I probably called them I when I was talking about the polarizations of a 4 vector. But in any case, if we let I label the possible polarization states, say X polarized or Y polarized for a photon propagating in the Z direction, then we have these polarization vectors that multiply the raising and lowering operators, A and A dagger. So here, A sub pi, for example, is the operator that creates a photon of momentum p and polarization epsilon I. Okay. So really the idea is that just as for charge fields, for the charge scalar field, I needed to tell you whether I have an incoming electron or a positron. When we talk about a vector field, I need to tell you what the polarization of the incoming state is. I need to tell you whether it's circularly polarized or, what is it, clockwise polarized or counterclockwise polarized, if you wanted to use that polarization basis. So the incoming states in our momentum space Feynman rules will be labeled not just by an incoming for momentum p, but also by some polarization vector. Okay, so what we now need to do is understand how we modify our Feynman rules in order to incorporate the fact that all of our incoming and outgoing states have polarizations. So if I wanted to do this super carefully, like in complete detail, what I would do now is I would go back to the LSZ formula, which I remind you was the formula that we used to turn position space correlation functions into scattering amplitudes. I don't want to do that because, first of all, it's sort of boring, and you can just essentially guess what the answer is if you just sort of think about it. The point is really that for each incoming state, we need simply a factor of the polarization of that incoming photon, epsilon mu. And similarly, for each outgoing state, we need a factor of the complex conjugate of that polarization, epsilon star. And the only slightly subtle thing here is the fact that you need to complex conjugate the polarization vector depending on whether you have an incoming or an outgoing particle. And that really comes from the, from the fact that if you wanted to say, describe an incoming state, you would act with this raising operator, which has an epsilon star. And if you wanted to write down the corresponding outgoing state, you would have to take the dual of that, which involves a lowering operator, each of which comes with a factor of the polarization vector epsilon rather than an epsilon star. So just to make this all completely explicit, so let me just end with a couple of examples. So let's imagine that we wanted to compute the amplitude for, say, an electron to scatter, so a photon to absorb with for a photon plus electron to become an electron. So this would be described by a Feynman diagram that looks like this. Okay. So here I need to label the incoming electron by some polarization vector. It'll have, the incoming electron will have, the incoming photon will have some momentum that I'll call K, and the incoming electron will have some momentum that I'll call P. And then the outgoing electron, by momentum conservation, will have a momentum P plus K. Remember, I'm using the convention that momentum is flowing from left to right in this diagram. So then what is this? Well, you get a minus IE from the interaction vertex. You get the polarization vector epsilon mu, and then we just have to remember our rule for how to incorporate the derivative interaction in this trivalent vertex where a photon combines with an electron. In particular, you get a minus sign for each momentum because in this expression, the particle flow is opposite to the direction of momentum flow. And so you would get a minus P mu minus P mu plus K mu. So that would be IE epsilon mu times 2 P mu plus K mu. Okay. Whereas, for example, if you wanted to write down the amplitude for an electron to emit a photon with a particular polarization state, then you would have a factor of epsilon star here instead of a factor of epsilon. Okay. So in fact, if you go through it carefully, here now you would have a P minus K. So you'd get a 2P minus K. Okay. Any questions on that? Yes.
Now, okay, so in order to talk about like why there has to be the complex conjugate of the polarization and so on, like when we talked before about similar things with charge, it was all based upon our like assumption that there's a symmetry in Lagrangian, which like symmetry with respect to this charge conjugation.
Right.
So that was the reason basically why we had to apply some rules
I mean,
to Feynman diagrams.
Right. I mean,
what's the symmetry now?
yeah. So it's not, okay. I mean, a comment that I'll make is that we could always choose a basis where our polarization vectors are real. So, for example, if you think about a photon moving in the z direction, then the polarization vectors could be x hat and y hat. That's sort of the usual choice for linear polarizations. And if that's the case, there's no difference between epsilon and epsilon star. It's just that sometimes people find it convenient to use circular polarization instead of linear polarization, in which case the polarization vector for a photon propagating in the z direction is x plus iy and x minus iy instead of x hat and y hat. And I guess there are various reasons why people like talking about circularly polarized and clockwise and counterclockwise polarized light, but that's really just a convention. And so there's no kind of symmetry. The vector field is a real field, okay? And that's reflected by the fact that this operator here is the Hermitian conjugate of that operator, right? If it weren't a real field, then those operators would not be Hermitian conjugates, and there would really be some symmetry associated with some charge rotation. But there's no symmetry associated with that. It's really just a kind of, it's really just the fact that by making polarization vectors complex, that's sort of a more convenient way of packaging the polarizations of a photon.
But we can't just, like, in our Feynman diagrams, we can't just have, like, any polarizations and don't take care about them. And like, there has to be a reason in the, like, the ground for that we need to care about this in Feynman diagrams. And I thought that could be, like, parity symmetry or something.
I'm not quite sure exactly. So what exactly do you mean? I'm not sure exactly what you mean.
Yeah, I think
I mean,
like formulate the lingo.
Maybe I should say it the following. Maybe I should say it the following way. If you took a mu and you acted it on the vacuum state, you would get epsilon star 8 times a dagger acting on the vacuum state. Okay. If you acted on the vacuum state, the ket vacuum state, but if you acted on the bra vector from the right, you would get an epsilon times a rather than an epsilon star times a dagger. So the reason why you get an epsilon, maybe this is the question that you're asking, the reason why you get an epsilon for initial states as opposed to an epsilon star for final states is really time reversal symmetry, if you like. It's because of the fact that initial states are ket vectors and final states are bra vectors, right? And if you imagine taking a field, if we went through the LSZ rules carefully for a vector field, this is what we would see. But it really comes down to the fact that whenever you insert an A in an expectation value, if it's multiplying a ket, you get an epsilon star, and if it's multiplying a bra, you get an epsilon. Okay? So I guess you could call it time reversal symmetry if you like. It's the difference between bras and kets. Good questions. Okay. Let me make one sort of final set of comments, which is that it's actually important to track indices carefully when we write down Feynman diagrams for particles with spin. So let me just, for fun, consider the following scattering process. Okay. So let's consider a state where we have one electron, or maybe let's call it a positron, coming in, along with a photon. And then let's say that coming out, we have 2 photons. And so you could imagine, that would be a sort of Feynman diagram that would contribute to this process. And let's see, we would have 2 incoming momenta and 3 outgoing momenta. So I'll call K the momenta of the photons and P the momenta of the electron. So all of our arrows have to align by charge conservation. And let's call these polarizations epsilon 1, epsilon 2, and epsilon 3. Then the important thing is I don't want to go through in complete detail, although it would probably be instructive. Would it be instructive? You guys have 5 minutes. Would it be instructive if I wrote down this guy in complete detail? The important point really is that you have to be careful to contract all of your indices in the sort of way that you're instructed to by these Feynman diagrams. Because really, you have these three polarization vectors. You have an epsilon 1 mu, an epsilon 2 star nu, epsilon 3 star rho. And the various terms that will appear in your Feynman diagram. So this total, this total Feynman diagram, what is that? That's proportional to e to the fifth, because you have an e squared here, an e squared here, and an e here. But if you look at how the indices are computed, what you have is, well, I don't want to go through in all sorts of detail, but you have some internal momenta here, P3 and P4. And you have an internal momentum here. Let's call that K4. And if you look at how the indices are contracted, what you'll see is that there's a, well, I don't want to go through it in all. I'm out of time, so I don't want to go through it in too much detail. But you have a factor of the metric here, along with a factor of the metric here. So that's going to end up contracting the epsilon 1 and the epsilon 2 vectors together. So you're going to get something like that. And then the epsilon 3 is going to be contracted with the momenta of these guys. So you'll get a P3 rho plus P4 rho. And then, of course, the momenta P3 and P4 are going to be determined by momentum conservation as being built out of P1, P2, K1, K2, and K3. Okay. So the only point of this is that we really need to be careful to keep track of how the indices all get matched up in these Feynman diagrams. And in particular, one implication of this sort of reasoning is that internal lines, that the indices in internal lines will get summed over. So for example, if you were to write down a diagram like this, what would you get? Well, you would have a 2i e squared. You would get a g mu nu from the interaction vertex. But if k is the momentum of your photon, you would have an integral d4k of g mu nu over k squared minus I epsilon. So this diagram has no external polarizations. And so if you think about it, summing over those internal indices is the only possible thing that could happen. Okay? So you'll just get an overall factor of 4, which is g mu nu contracted with g mu nu from that Feynman diagram. Okay. I just want to point these sort of things out now, because these are the sorts of things that will appear when we start considering, more complicated kinds of Feynman diagrams in quantum electrodynamics. And I just sort of want to point them out now in the relatively simple theory of scalar QED before we get to the full glory of quantum electrodynamics. Okay. I should probably stop here. Sorry for going over time by a few minutes.